Hello everyone, welcome to the 7th video of our lecture series. So let us start with our first problem. So the problem states that we have a one-dimensional harmonic oscillator and we know that 0, 1, this represents the normalized eigenstates or normalized energy eigenstates corresponding to the ground and fast excited state. So we have to find the uncertainty delta p in the state this. So let us proceed. So we are given with the state this. So this is our initial state of the system, and we have to find delta p for this state. So how we will find delta p? So we know that delta p or uncertainty in p is defined as expectation value of p square minus expectation value of p whole squared. So we have to find these two quantities. So we know that in case of harmonic oscillator, we can define this position operator and momentum operator in terms of raising operator and lowering operator. So how we will write this? So basically we know that P is defined as I m omega h cut by 2 a dagger minus a. So that is how operator P is defined. So first let us find expectation value of P. So that means we have to find this quantity psi P psi. So let us first calculate this P psi. So P psi will be I m omega h cut by 2 a dagger minus a, and we have psi to be 1 by root 2, so multiply this with 1 by root 2 and we have this 0 plus 1. So let us evaluate this. So I m omega h cut, we have 2 here, and when this raising operator will act on 0 state, it will be 1, and for this one, so it will be root under 2 product with 2, and when lowering operator will act on the ground state, it will give us 0, and when it will act on state 1, it will give us 0 state. So let me write down the operator, how operator acts on state, so it will be easy for you. So a dagger on a will give us root under n minus 1. So it will give us root under n multiplied with n minus 1, and raising operator acted on state n will give us root under n plus 1 multiplied with n plus 1. So these are the two formulas that we have used here. So from this we will get I m omega h cut by 2, we will have 1 minus 0 plus root 2 multiplied with 2. So what will be psi p psi? It will be I m omega h cut by 2 root 2, and psi we have 0 plus 1, so that we have to operate on this. Now since this n state ends, they are orthonormalized, so we can write So first term will give us 0, second term will give us minus 1, and this will also be 0, and this term will give us 1, this will be 0, and this will also be 0. So we have 0. So the expectation value of momentum operator is 0. So now we have to find expectation value of p square. That means psi p psi. Now psi we know, psi is I m omega h cut by 2 multiplied with 1 0. Oh, so this will be plus root 2 into 2. So if we again add p operator on this, so let us operate p on p psi. So p we know is defined as this. So it will give us I root under m h cut omega. So we have root 2 here again, and for this term will be there I m omega h cut by 2, and p we know, p we have a dagger minus a, and we have here 1 0 plus root 2 2. So we have m omega h cut by 2 root 2, and let us evaluate this. So first add the raising operator on this. So first term will give us root under 2 2, second term will give us 1, third term will give us root under 6 3, and now add this lowering operator on this. So first term will give us 0, second term will give us 0, this will be 0 state, and this give us value 0, and the last term will give us minus 2 1. So that is what we are getting. So if we simplify this, we will get minus m omega h cut by 2 root 2, and here we have root 2 2 minus 3 1 minus 0 plus root 6 into 3. So if we do the calculation for this quantity, we will get minus m omega h cut by 2 root 2 into root 2, and we have here 0 1, and here it will be this. So just simplify this one. So again, using the orthonormality condition, this will be 0, second term will also be 0, third term will give us minus 1, and fourth term will give us 0, and here first term will give us 0, second one will give us minus 3, third one will give us 0, and fourth one will also give us 0. So what we are getting here? We are getting here minus m omega h cut by 4 multiplied with minus 4. So we are getting m omega h cut. So we have delta, we have p squared average to be m omega h cut, and we have p average to be 0. So what will be the uncertainty? Uncertainty, just let us put this value in our formula, so we will get our desired result. So this is root under m omega h cut. So root under m omega h cut, that should be our uncertainty in p. So let us check the options. Yeah. So our correct answer is this one, C. So in this similar way, you can calculate uncertainty in X for different states. You can calculate. Just write this in terms of raising and lowering operator and use this formula. Then we will get our desired result. The uncertainty we can calculate in position, momentum, or any other operator. Now let's move to the second problem. So in the problem, so what the problem states? It states that we have a hydrogen atom wave function and it is given as this. So here N, L, M, they are usual quantum numbers. So what is N? N is principal quantum number. So it basically represents electron shell. After that we have L. So L is azimuthal quantum number. Or orbital angular momentum quantum number. So it basically represents sharp shell. Now suppose like S for, and we have P and all this, etc. So what can be the L value? L value is between 0 to n minus 1. And after that we have M. So what is M? M is magnetic quantum number. And for orbital angular momentum, the magnetic quantum number ml, it can be from minus L to L. So these are the usual quantum numbers by which we are defining the wave function of a hydrogen atom, and the wave function is given here. So what we have to find? We have to find the ratio of expectation value of the energy to the ground state energy and the expectation value of L square. So we have to find here two things. First, we have to find the ratio of expectation value of energy to the ground state energy, and second, we have to find the expectation value of L square. Okay, so we know that the energy, I mean the Hamiltonian and L square, they commute. For hydrogen atom, H and L square commute. That means they have the same eigenstates. So this psi NLM, their eigenstate of H, also eigenstate of L square. So what is the eigenvalue for H? So it will be E0 by n squared psi NLM. So what is E0? E0 is the ground state energy of hydrogen atom. And we have L squared psi NLM, which will give us the value L into L plus 1 H cut square to we have psi NLM. So that is the eigen values for these two operators, Hamiltonian operator and L squared operator. So as we have to find the expectation value, so we have to find these two quantities, psi H psi, and we have to find psi L squared psi. So what is our given state of the system? So our given state is, so let us write this in bracket notation. So it is root under 2 by 7 100. I'm writing psi 100 r as 100 for convenience, and the second term we have 3 by 14 210, and the last term we have 1 by 14 322. So these are the values of NLM for different eigenstates. So let us calculate 8 psi. So what will, for first one we will have, this is our value n, so we have E0 by n squared. For second term we have n value 2, so it will give us E0 by 2 squared into 210, and for the last term we have n value to be 3, so we will have E0 by 3 squared, so it is multiplied with 322. So now let us calculate this quantity, the expectation value of Hamiltonian. So what will be the result? So we have 2 by 7 into E0 plus 9 by 14 into E0 by 4, and we have 1 by 14 E0 by 9. So if we do the calculation, it will turns out to be 229 by 504 E0. So what will be the ratio of expectation value of energy to the ground state energy? That means we have to find, so if we denote this by E, then we have to find E by E0. So what is E by E0? E by E0 comes out to be this. So this is the ratio of the expectation value of the energy to the ground state energy. And now we have to find the expectation value of L squared. So let us do that. So L squared psi, what it will give? So it will give us root under 2 by 7. So for the first term we have L value 0. So that means it will give us 0 into 1 h cut square, and we have 100, and in the second term we have 3 by root 14. So for the second one we have L value to be 1, so we will have 1 into 1 plus 1 h cut square, and here we will have 210, and similarly for the last term we have L value to be 2. So here we will get 1 by root over 14 2 multiplied with 2 plus 1 h cut square 322. So what will be psi L squared psi? It will be 2 by 7 into, so first term we are getting 0. So and from the second term we are getting 9 by 14 into 2 h cut square, and from the last one we are getting 1 by 14 into 6 h cut square. So that turns out to be 24 by 14 h cut square. That means 12 by 7 h cut square. So that is the expectation value of L squared. So let us check. Yeah, so the correct option is the first one. So what we have learned, so basically we are given the wave function of a hydrogen atom. So and in the wave function for we are given the different quantum numbers value. So here we have to find the expectation value of the L squared operator and Hamiltonian operator. So and as Hamiltonian and L squared operator, they commute, so that is why they share the same eigenstate, so that psi NLM, they are eigenstate for both the Hamiltonian operator and also for L squared operator. So now let us move to the third problem. So the problem states that the component along an arbitrary direction n cap with direction cosines nx, ny and nz of the spin of a spin half particle is measured. So we are measuring the spin of a spin half particle along any arbitrary direction. So what will be the result? Like what will be the value that we will get? So we know that in the S square and Sz basis, this Sx, Sy and Sz are defined as 0, 1, 1, 0. Sy is h cut by 2, 0 minus I 0, and Sz is h cut by 2, 1, 0, 0 minus 1. So we can write spin as, so let me use this is just an operator. So we can write Sx I cap plus Sy j cap plus Sz k cap. So this is our spin, and since n is any arbitrary direction with direction cosine this, so we can write n as nx I cap, ny j cap plus nz k cap. So since these are direction cosines of an unit vector, so nx square, ny square plus nz square, that must be 1. So now let us calculate the component of the spin along any arbitrary direction. So component of spin along n. So we have to find the dot product between s and n. So this will be equal to nx sx plus ny sy plus nz sz. So we will have nx nz h cut by 2. Here we will have h cut by 2 nx minus I ny. Here we will have minus nz h cut by 2, and here we will have h cut by 2 nx plus I ny. So this is our matrix. So we have to find what if we measure this s dot n, so what will be the value we will get. So that means we have to find the eigenvalue of s dot n. So let us calculate the eigenvalue. So if lambda is the eigenvalue, then the equation to get the eigenvalue will be nz h cut by 2 minus lambda h cut by 2 nx minus I ny h cut by 2 nx plus I ny, and here we have minus nz h cut by 2 minus lambda. So that is the determinant which we have to solve to find the eigenvalue. So from here we will get lambda square minus nz h cut by 2 squared equal to h cut by 2 squared, and we have nx square plus ny square. So if we simplify this, we will get lambda square equal to h cut by 2 squared, and we have nx square plus ny square plus nz square, but this term is 1. So what we have, So we have lambda is plus minus h cut by 2. So if we measure spin along this direction, then what will be the values that we will get? So we will get value plus minus h cut by 2. Okay, so here the correct answer should be this one, plus minus h cut by 2. That is the value that we will get if we measure the spin along any arbitrary direction n cap with direction cosine this.